Okay, um, brand new week. We hopefully by this point we have a good grasp on balancing equations and moles, and that's going to be the big deal. Our basically between now and Halloween, we're going to be spending some time on something called stoichiometry. I got a few other topics to talk about. Stoichiometry, which is I think is a Greek word for stuff that students really can't understand that well. That's actually not what it means. It means sort of the counting atoms and the algebra of chemistry. But for some reason, students, it's a new way to look at things. But we might get started on it today, and if not, we'll just hit it tomorrow. But there are some vocabulary words here that I want you to learn, and those are chemical and physical properties. So you want to jot those down, and chemical and physical changes. And they're very simple uh, concepts conceptually, so we won't be spending a lot of time on them. Chemical and physical properties of different materials have to refers to, for example, a physical property might be something like, is something a gas, a liquid, or a solid at room temperature? So that would be a physical property. A physical property would be something like, is it is it brittle? In other words, if I have something like a chunk of sulfur and the beautiful uh, yellow colored material, if I hit it with a hammer, it'll just like it's just like smash. It'll get crushed and it's very brittle. If I have a crystal of sodium chloride, the sodium chloride is the same deal. It will smash, and if I hit it, it's not malleable like a metal. Metals are malleable. You can hit them with a hammer. If I have, let's say, I have some, I have some iron, and I heat them. I heat the iron up in a furnace, and I can hit it, and it'll be able to be drawn into wires or form different shapes. So those are physical properties. Chemical properties, on the other hand, are those properties that uh, refer to the I hate to use a word to define something, but the chemical nature of an element. So let's say, for example, I take a chunk of sodium metal and I throw that sodium metal in some water. We'll have to do that before the end of the week. It's always fun to watch. You see a very violent chemical reaction, and it's very highly reactive because it has. We're going to learn shortly. Well, maybe after we get through stoichiometry, about the electronic configuration and properties of sodium. It's got this electron and it wants to get rid of it, so it's a very violent reaction, and it's a lot of fun to watch. On the other hand, if I take that chunk of sulfur I talked about and throw it in water, it's not going to react. Some gases, in the noble gases, helium, neon, argon, and krypton, they don't react at all. So their chemical properties are pretty boring. So just so you understand the difference, chemical properties deal with how chemicals react. Physical properties deal with things like color, melting point, boiling point, just things that don't change the material chemically. And that leads us into some of our uh, other topics here, like chemical and physical changes. Physical changes, for example, would be just something like melting H2O. I have H2O, and it's an ice cube, and then I melt it, and it turns into water. I can freeze it, and it turns back into a solid. That's a uh, physical change. On the other hand, if I take water and I pass an electric current through it, I can separate it into oxygen and hydrogen gas. So that's a chemical change. A physical change would be something as simple as cutting your hair, right? Doesn't change the composition of your hair. I'm just changing the length of my hair. I'm cutting it. But a chemical change is if I caught my hair on fire, which I certainly don't want you to do, but then you're actually carrying out a chemical reaction, which is very nasty. So I'll have a little reading in your book. You can look at some examples on chemical and physical properties and chemical and physical changes. So again, doesn't take a lot of mental hijinks to understand that, I don't think. And we'll take a look at some of those things in the book. Let's take a look next, though, at types of chemical reactions. And when we look at the equations that we had to balance, I don't know if you noticed, but there certain types of things kept reoccurring. And if we look at every chemical reaction on a sheet, say I have this sheet, and I look at all these chemical reactions, and we try to look at everyone like it's a brand new reaction, you'd go crazy. So we classify them according to reaction type. So let's take a look at the 5 fundamental types of chemical reactions. And this is something I'd like you to pay attention to this. This is a little bit more important than chemical and physical changes, maybe a little bit more difficult to wrap your mind around. But hopefully, by looking at chemical reactions, we can figure out what type about which we are concerning ourselves. So the first type, combustion. And these are in no particular order. I just list them the way I think of them. Combustion, and some people would just call that burning. So whenever we have substances that are, I'm just going to put something like CnHm. This would be called a hydrocarbon. A hydrocarbon. Or we might have something that is a CnH MOH. I have an OH on it. This would be an alcohol. So, for example, something like C2, I have to draw it out. C2H5OH. That's ethyl alcohol. So anyone who's watched a chef maybe put some brandy in a pan and flip that pan, and the brandy burns. You see that those flames. That's an example of a combustion reaction. Other things that can burn would, well, there are many things, but if you look at things like sugars, maybe C6H12O6, carbohydrates. Carbohydrates. They will all undergo combustion reactions. And there are other chemical compounds. But what do you notice about a lot of these chemical compounds? They all have carbon and hydrogen, and you know, this could be something like octane that's in your gasoline. So what is a combustion reaction? It's taking either a hydrocarbon, alcohol, carbohydrate, these types of organic compounds, reacting them with oxygen, and you always get the same products. You always get CO2 plus H2O. So if you see a reaction and I give you let's say on a quiz I say identify the following type of reaction, and maybe we have something like this: C8H18, that's octane, and we react it with oxygen, and then you balance it, of course, CO2 plus H2O. And this would be easy. Want to balance it? We have 8 carbons. We've got 18 hydrogens, so we put a 9 there. So then on my number of oxygens, I've got 16, and 9 is what, 25? Yep. So then I have to put 25 over 2, and I can clear the fraction, and I'd have the balanced equation 2CH18 plus 25O2 gives 16 CO2 plus 18 H2O. And I said, hey, what type of a reaction is that? Well, you look at it, you balance it, you look at it, you say it's a hydrocarbon reacting with oxygen to give CO2 and H2O. So that's a real easy one to recognize, I think. Look for the products. If I'm getting CO2 and H2O, and I'm reacting something with carbon and hydrogen and oxygen, that's a combustion reaction. So pretty easy to identify that. Okay. Double replacement reactions. Double replacement reactions occur when you mix two inorganic salts. Now, first of all, I used a word here. I used two words, inorganic salts. Another name for ionic compounds are salts. We think of sodium chloride, table salt, put it on my whatever, and that's certainly one type of salt. But anything can be a salt, like KCl, potassium chloride is a salt. Um, you name it. I mean, calcium bromide is a salt. And ionic compounds, we're going to see, have some really unique properties. But let's say I take some silver or some potassium chloride and I react it with silver nitrate, which is also an inorganic salt. By the way, inorganic meaning it's not carbon based like the hydrocarbons or the carbohydrates about which we just spoke. So something in a double replacement reaction takes place, and it's very interesting. Who went to homecoming? Well, let's pretend. I'm just going to use, no, don't, I'm not trying to be offensive or anything. This is just a demonstration. Let's say that Wyatt went with Carly. Let's just say that you guys went to homecoming. And let's say that Christian went with Maddie. Okay. And you guys were sitting at a table and you decided that, well, I don't really like my date. No offense, Wyatt. You just don't like your date. And he's like, I don't really like my date. So you switch dates. So Christian ends up going to homecoming with Carly, and you end up going with Maddie. You switched. Okay. Same exact thing happens here. Potassium goes with chloride to the homecoming and says, boy, I really got my eye on that nitrate. They're beautiful. Silver says, okay, chloride, not that bad. So they switch partners. That's a double replacement reaction. Interestingly, though, and again, that's just an analogy. Again, I'm not trying to make any statement about anything. I hate to have to say that in the 21st century. Back, 10 years ago, you could just say those examples and not have to worry about it. One of the things that will happen, though, is this is an aqueous solution, this is an aqueous solution, and you're going to get something that comes out of solution that separates and usually forms a solid, usually, and we call this a precipitate. Matter of fact, I'm going to pause this and I'm going to show you an example. So what we did there, I should have done it on the recording. Maybe I'll have to do that. But we took some stuff that was we took some lead nitrate. It's pretty neat, isn't it? Let it set; it'll all fall to the bottom. We took lead nitrate, which is an aqueous solution, and you saw it. It was colorless and clear. Looked like water, and I reacted it with uh, sodium iodide, which was aqueous, and the yellow material that we got was lead iodide. That turned into a solid. Plus, we get the sodium nitrate, and I get two of those, and that remains in solution. So recognize double replacement reactions when they switch partners. They switch partners. Not too bad. single replacement reactions. Okay, single replacement reactions is that you have a compound plus an element to give different compound plus a different element. So if I have something, for example, and I want to carry out a chemical reaction, maybe I have something like NaCl, and I react that with Br2. Okay, this is a compound, sodium chloride. This is an element. So you react, and what ends up happening is the anion, most times, will become the new element. It'll revert to its elemental form, and then this will become an anion. So I might end up with something like this: 2 sodium bromides plus Cl2. A compound plus an element gives a different compound plus a different element. Pretty easy to recognize. And we'll go ahead and we'll take a look at our balancing worksheets and try to identify these things. All right, how are we doing here on time? We're getting there. Synthesis reaction. Synthesis reaction. Synthesis means bringing things together to form a new compound. The Haber process, there was a German scientist named Fritz Haber, and he was looking for a way to make ammonia gas. So he took nitrogen and hydrogen, H3, no, not in this universe, to give NH3, and he synthesized a compound from these two other, in this case, elements. Bringing two things together to form one thing is a synthesis reaction. And this we may watch a little video about this process. It's kind of interesting. And the guy who came up with this, Haber, Fritz Haber, as Dylan and I were talking about this morning, became sort of the father of explosives and biological weapons because of some of the processes that he came up with to synthesize ammonia. So even though he did a great thing, because you need ammonia to help fertilize things and whatnot, also this led to some pretty bad things as well. But such is science. So the opposite of synthesis is taking one thing and breaking it apart. So if I have something like calcium carbonate, okay, let's write what this is. This is called a decomposition. Decomposition reaction. I take something like calcium carbonate and maybe I heat it up. Okay, that little delta sign above the arrow means heat it up, and I get calcium oxide plus CO2. I'm taking one thing and I'm breaking it into two things. And that's called decomposition reaction. So we've got the following types. Combustion, double replacement, single replacement, synthesis, and decomposition. So we'll take a look at these on the back of our sheet if you still have it, and then we'll see, and if you don't, I'll write them up on the board. We'll see if we can identify these reaction types. I do want to talk about one other type of a double replacement reaction, which is sort of a sub classification of double replacement, and that's acid base reactions. And I'll show you what I mean for an acid base. Remember, double replacement is where they switch partners. So same thing happens with an acid base reaction. I have something like HCl, hydrochloric acid, and I react it with sodium hydroxide. And make a note of this in your notes, for acid-base reactions, you react an acid with a base and you always get the same products, a salt and water. And the salt, since it's double replacement, is going to take that anion, so I'm going to have NaCl, and the other thing, that H is going to go with that OH, and I'm going to get H2O. So it won't always be sodium chloride. It just happens to be sodium chloride in this example. Good. All right. So do you still have your balance equation sheet, or should I just write them on the board? You got them? Okay. I'm trying to see which one you have here. Yeah. Anyway, I'm gonna put this online, so